Okay, hello and welcome back. In this video, we are starting chapter 6, so we're covering section 6.1 on the addition and subtraction of polynomials. So you'll see polynomials a lot in college algebra, so it's really important to be comfortable working with them, understanding what they are, and how to combine them together, add them, subtract them, multiply, and divide. And this will ultimately lead us to the topic of factoring, which we'll see in chapter 7. So for the remainder of this course, we'll be working with polynomials and understanding their properties. So we'll start today just defining what a polynomial is. It has some vocabulary associated with it. We'll practice evaluating them, which will just be plugging numbers into them. How to add and subtract polynomials with each other. We'll look at some examples when we have more than one variable, and then we'll define and evaluate a polynomial function, so using some function notation. So let's first define what we mean by polynomial. So the textbook gives us this definition. They say a polynomial in X. When they say that, they mean that X is our variable. It could be any variable we want. So a polynomial in X is the sum of a finite number of terms of the form a times x to some power n, where n is a whole number, meaning the exponent is not negative, it's some whole positive number, and a is a real number, meaning it's not imaginary. Let's see a couple specific examples. So something like 3x squared plus 2x plus 1, or x to the 6th power plus 2x squared minus 3, or even something like 3x plus 1. These would all be examples of polynomials. You have the sum or difference, so plus or minus, in between a bunch of terms that look like some number times our variable x raised to some power. And you may be asking, well, what about this positive 1 or this minus 3? Technically, we have x raised to the 0 power attached to it. That's one way of looking at it. So you can have some constant number. Constant meaning that it is not attached to any variable, and if we were to plug in some value for x, that constant number would stay the same. It wouldn't change. It would remain constant. So that's one vocabulary word we can add here. Some constant term. The 3 and the 2 in this example, we would call those coefficients, so the numbers in front of your variable. The highest power that we see, in this case, the highest power in the expression is 2, is the degree of the polynomial. So I would say this is a second degree. And then the coefficient on the variable with the highest power, we can call that the leading coefficient. Oftentimes a polynomial is put in this descending order, meaning you have your highest power, then your second highest power, and then it goes down from there. So the coefficient attached to the variable with the highest power is the leading coefficient, oftentimes because it will lead the expression. It'll be placed first. So in the second example, we would have a 6th degree polynomial. Notice we don't have a 5th degree component or 4th degree. It jumps straight from the 6th power to the 2nd power, and that's okay. It still makes it a polynomial, as long as the exponents aren't negative. And even this last one, there's technically a 1st power next to that x. You should recognize this as the equation of a line. So a line linear equation is a 1st degree polynomial. So you can view it as a whole class of expressions that have this general structure. And we can work with these. We can add them together, multiply them, subtract them, divide them. So that's what we'll be exploring. Just to add a few more vocabulary terms, depending on how many terms in the expression we can have special names. So, for example, if it has one term, we can call that a monomial. Monomial, like mono for one. So an example would be like 3x to the first power. If we have two terms, we can call this a binomial. So like x squared plus 3x. Two terms, that'll be a binomial. And if we have three terms, we can call that a trinomial. So like 8x cubed plus x squared plus 3x would be a trinomial expression. And we can have as many terms as we want, but for the first three cases here, we have some special vocabulary. Maybe for the fourth term, we can call it a quadrinomial. So our first example just has us determine whether or not an expression is or is not a polynomial, and then to find the degree of the polynomial. So in example A, we have negative 8p to the fourth power plus 5.7 times p cubed minus 9p squared minus 13. So for it to not be a polynomial, I would just need to see some negative exponents, or maybe an imaginary number in front of our variable. We can have a negative coefficient or a fraction or a decimal, that's okay. And we don't have any negative powers, so I would say this one is a polynomial. And the highest power I see is the fourth power. I'm going to say it's a fourth degree. Part B, we have 4 times c squared minus 2/5 times c plus 3 plus 6 over c squared. So we have that c squared in the denominator. If you remember, we can express that as a negative exponent. So instead of 6 over c squared, I can write this as 6 times c to the minus 2 power, to borrow that rule of exponents. And that's the thing that will break our rule for polynomials. So polynomials need to have a positive exponent. So I can say they don't have negative exponents. There's nothing wrong with having this here, it just doesn't classify this expression as a polynomial. Part C gives us a cubed times b cubed plus 4 times a cubed times b squared minus a times b plus 1. So we have more than one variable here. We have a and b, but we still only have positive exponents, so this will still be considered a polynomial. And if you have two variables like this, the degree will be the sum of the two powers. So we would say this is a degree 6. So 6th degree, this would be a 5th degree for our second term. 2nd degree, since we have two ones for the third term. So the highest one there is the 6. And part D just has a single term, so we have a monomial 7n to the 6th power. Still is a polynomial. It has a degree of 6. So we could be asked to evaluate a polynomial, which really just means to plug in a number. So we're given this trinomial n squared minus 7n plus 4. It's called a trinomial because we have 3 terms here. So we want to evaluate when n equals a couple different values. So we just need to plug that in. I can say when n equals 3, well, that would give us 3 squared minus 7 times 3 plus 4. 3 squared is 9. 7 times 3 is 21. So 9 minus 21 plus 4 should give you a negative 8. Now let's evaluate. We can evaluate for a negative number when n equals negative 2. When I have a negative, I just got to be sure that I'm evaluating things correctly. So it's really helpful to use parentheses. So like this is going to be negative 2 squared. So that tells me the negative will get squared as well. Minus 7 times negative 2 plus 4. Negative 2 squared will be positive 4. Then I have negative 7 times negative 2. So that double negative will cancel and give me a positive 14. And then plus 4. Which will add up to 22. So just be careful with the negative. The negative gets squared, and then here we have the negative times the negative, so everything ends up positive. So that's evaluating a polynomial, really just plugging in a number. And so we can add and subtract them together, whole polynomials, as objects themselves. They tell us to add a polynomial, just add like terms. So like terms would include variables, like components that have variables with the same power. And then constant terms can also be added together. So let's see a couple examples. So our first one we have m cubed minus 9m squared plus 5m minus 4. So that's one whole polynomial. I have it in parentheses. Plus 2m cubed plus 3m squared minus 1. So one whole polynomial plus another polynomial. So we'll end up adding together all terms that are alike, meaning these m terms with the third power will combine together, the second powers will combine together, the constant terms will combine together. So it's helpful to rewrite this with the pairs together, meaning we can rearrange this as m cubed plus 2m cubed, so putting those together, then minus 9m squared plus 3m squared plus 5m. There's no other term with m to the first power, so that one's on its own. Then we have minus 4 minus 1. So I'm just rearranging things so that I can add my like terms together. This helps me see what will combine. So 1m cubed plus 2m cubed will give us 3m cubed. We have negative 9m squared plus 3m squared. So that will give us negative 6m squared, negative 9 plus 3. We have that lonely 5m, which will stay the same. And then negative 4 minus 1 will give us negative 5. So we just want to combine like terms together. Right, example 4, we have 10k squared plus 2k minus 1, and we want to add 5k squared plus 7k plus 9. So I can combine, or at least place them together first. So 10k squared plus 5k squared. Then we have the 2k on the left and the 7k on the right, and then a minus 1 and a plus 9. So 10k squared plus 5k squared will give us 15k squared. 2k plus 7k will give us 9k. And then negative 1 plus 9 will give us a positive 8. So again, just adding like terms together. Just keep in mind you can only combine variables that have the same power. They will add together. So that's adding. We can also subtract polynomials from each other. So in the textbook's procedure, they say to subtract two polynomials, change the sign of each term in the second polynomial, then add them together. What do they mean by this? Basically, we're distributing the negative to each term. Let's look at our first example. We have 8x plus 3 minus this whole second polynomial, 5x minus 4. So we just need to be sure that this negative applies to every term. We're subtracting this entire thing. It's tempting just to write this as 8x plus 3 minus 5x minus 4. However, that would lead us to an incorrect result. This negative is going to distribute. It's like being multiplied by the second polynomial. So imagine the negative hitting the 5x, so that will make the negative 5x, but the negative also distributes to the second term. So minus negative 4 will actually give us a plus 4. So the subtraction will effectively just flip the sign for each term in the second polynomial. That's what they're describing in that procedure. So once we've distributed the negative, then we can just combine these together. So I can see that 8x will combine with the minus 5x. And I have a positive 3 and a positive 4. So 8x minus 5x will give us 3. And 3 plus 4 will give us 7. So 3x plus 7. So the main thing to keep in mind is that the negative distributes to every term. It's an easy mistake to make to just end up subtracting the first term and then leaving everything else as it is, but it'll end up changing all your negatives to positives and positives to negatives in the second polynomial. All right, let's see a slightly more complicated example. We have minus 6w cubed minus w squared plus 10w plus 1 minus, in parentheses, 2w cubed minus 4w squared plus 9w minus 5. So let's distribute that negative to every term in the second polynomial. First one will stay the same, minus 6w cubed minus w squared plus 10w plus 1. So this will give us minus 2w cubed plus 4w squared minus 9w plus 5. All the signs will change. Now we can add this together like in our previous examples. So I can put the w cubes together, and I have minus w squared plus 4w squared plus 10w to the first power minus 9w to the first power plus 1 plus 5. Now let's combine our like terms. So minus 6 minus 2 will give us minus 8 w cubed. Then minus w squared plus 4w squared, so minus 3w squared. And we have plus 10w minus 9w, so plus 1w. And then 1 plus 5 will give us 6. This problem mentions adding these or subtracting these vertically. So it's just another way to visualize this. Like we still have our first polynomial. We turned the second one basically into addition after distributing the, oh, I need to actually look at the previous one. So let's look here. And then we have our second polynomial. We could write these vertically like minus 6w cubed minus w squared plus 10w plus 1. And we're adding our second one, minus 2w cubed plus 4w squared minus 9w plus 5. And we can add these vertically, meaning we'll just add the vertical columns. So starting on the right, 1 plus 5 gives us 6. Then we have 10w minus 9w, so plus 1w. Minus w squared plus 4w squared, so plus 3w squared. Oh yeah, that should have been a plus up here, looks like. So plus 3w squared. And then minus 6w cubed minus 2w cubed will give us the minus 8w cubed. So just to show that you can have two different ways of visualizing the addition. And yeah, I caught a little error there because we had minus 1w squared plus 4w squared. That should have given us a positive 3w squared as opposed to a negative. Just double checking the rest now. Yeah, plus 1w plus 6. So we can also do this if a polynomial has more than one variable. We still just need to combine like terms. So let's look at this first one. We have a squared times b squared plus 2a squared b minus 13a times b minus 4. And we're adding 9a squared b squared minus 5a squared times b minus a times b plus 17. So like terms will have the same variable for, or the same power for both of your variables. So let me rearrange this a little bit. So on our first term, our first polynomial, we have a squared b squared. And in our second one, we have 9a squared b squared. So those will combine. Then we have 2a squared b. In our second one, we have minus 5a squared b. So those will combine. Then we have minus 13a times b. Our second one, we have minus another a times b. Those will combine. And we have minus 4 plus 17. So this should give us 10a squared b squared because we had 1 and then we added 9 more. Then we have plus 2a squared b minus 5a squared b. So 2 minus 5 will give us negative 3a squared b. Then minus 13ab minus another ab, so minus 14ab. Then we have minus 4 plus 17. So that should leave us with a positive 13. So same idea, we just need to have the same variables and exponents for both of the variables. And those terms can combine together. So let's see part B. We have 6 times tu minus t plus 2u plus 5 minus 4tu plus 8t minus 2. So we have a subtraction. I will first distribute that negative to every term in the second polynomial. So 6 times tu minus t plus 2u plus 5. So I'll have minus 4tu minus 8t plus 2. Let me pair my like terms together. So I have 6tu minus 4tu. I have this minus 1t, and on the right polynomial I have minus 8t. I have the 2u on the first one, and there's no u term that just has a u on my second one. And then I have plus 5 plus 2. So this should give me 2tu minus t minus 8t should give me minus 9t. Just have this lonely 2u, then plus 5 plus 2. 5 plus 2 is 7. So again, just combining like terms. All right, our last section has us define and evaluate a polynomial function. So it says a polynomial function of degree n is given by this big weird general expression. What we have is really what we've been working with so far, so a series of x's to some power with some coefficient. They're just using this new name for it, f of x. That's this notation here, meaning it's some function where x is the variable. So they say f of x, our function, is equal to x cubed minus 2x squared plus 4x plus 19. So the right side looks familiar. That's a third degree polynomial. We've been working with those. We're just giving it a name. We're calling it f of x. And so when they say to find f of negative 3, notice the negative 3 is replacing the x in that notation. all this means is plug in -3 for x. Meaning if I'm trying to find f of -3, well, everywhere on the right side, I'm going to plug in the -3. So it's like where we started with evaluating the expression. We're evaluating it for some chosen x number. So -2 times -3 squared plus 4 times -3 plus 19. Oh, and this should be -3 to the third power. So -3 cubed will give us -27. Then -2 times -3 squared, that will be a +9. Plus 4 times -3, you can already write that as a -12. Plus 19. So that means this should be -27, -18, -12 plus 19. If we combine all those together, you should get -38. So we can say f of -3 equals -38. This is new notation most likely. If you haven't seen this before, it's called function notation. You'll see that a lot in college algebra and in classes beyond that. It's really just a label. It tells you what your variable is. So some function of x, like when we say this is a polynomial in x. And then it gives us this notation to be able to say, without any like written words, to evaluate the function for a given value of x, meaning to plug in that value everywhere there's an x in your equation or your expression. All right, that's it for this section. So we explored some of the vocabulary around polynomials to find what they are, evaluated them, so plugged in some number. We did addition and subtraction. We saw some examples with more than one variable, and then introduced slightly the function notation and evaluated a polynomial function. All right, that's it for this video, and I'll see you next time.